Welcome back to Applied Mathematics. In this video, we're going to be talking about the trigonometric ratios. The idea of trigonometry builds off of the idea of similar triangles that we've talked about previously. Right? The root word trigonometry is the study of three-angled things. So the study of triangles is the study of trigonometry, and it makes sense it's going to build on the things we've already talked about with triangles. Let me get my head out of the way, and I'll show you what I mean. We know that if we have two triangles, let's say ABC and XYZ here, and we set it up so that measures of angles match up. Let's say that the angle at A and the angle at X match up, and angle B and angle Y are both right angles. If that's all we know about the triangles, right, the measure of angle A is equal to the measure of angle X, and the measure of angle B is equal to the measure of angle Y. But since the three angles in any triangle have a total measure of 180 degrees, since we know these two angles, the angle here at C is predetermined. It's 180 minus the measure of angle A minus the measure of angle B. And the measure over here at Z is predetermined. It's 180 minus the measure of angle X minus the measure of angle Y. And since A and X are the same, and B and Y are the same, then this whole right-hand side is the same, right? A and X are the same, B and Y are the same, and 180 is the same as 180. So that means that the third angles must be matching as well. And so we have that all three angles of these triangles match up. And I can claim that the triangles are similar. Right? Triangle ABC is similar to triangle XYZ. Now, because we have similar triangles, the lengths of corresponding sides are in proportion. So we can set up a ratio like AB over BC is equal to XY over YZ. And AC over BC is equal to XZ over YZ. And we can keep going, right? Anytime we choose two sides of one triangle, we can find the corresponding two sides of the other triangle, and they are similar to each other. All right, we've talked about similar triangles. That's old hat, that's familiar to us. The key thing that I want to add in here is that if we have that situation of given two angles, then that really determines everything there is about a triangle. One of the nice things we can do with a proportion is if we have several similar triangles, then the lengths of all of the sides are in proportion. We can calculate what that proportion is and call it a number. That's what trigonometry is. That's all that trigonometry is. Well, that and the consequences that come from it, which are well beyond what we're going to have time to talk about in the next several videos at least. But we've set up what we're going to call some prototype triangles. We need a triangle. We need that triangle to have a right angle on it. And we need to know the measure of one of the other angles in the triangle. Typically, we are going to mark that angle and call it theta. Right, the Greek letter theta kind of looks like the letter O with a belt on it. And the whole idea of Greek letters, they've come up a couple of times already. We kind of run out of letters, so we look for something else that we can use. All right. But as soon as we know that, as soon as we know we have a right angle and we know the measure of one other angle, we know that any other triangle that has this setup is going to be similar to it. And so if we take the ratio of any two sides of this triangle, it's going to be the same as that ratio for the same or for the corresponding two sides of any other triangle. And since I didn't give any letters to this, I'm going to go ahead and use what we usually use in trigonometry. We're going to call the three sides of the triangle op, adj, and hip. It's the opposite side and just gets abbreviated as op because, lazy. It's the adjacent leg and it's the hypotenuse. All right. We know that the hypotenuse of a right triangle is the side that's furthest away from the right angle. That's nothing new. We know when we use the Pythagorean theorem that the two legs of the triangle are interchangeable. It doesn't matter which one is which. But now we have a little bit more information, right? We have this particular angle as the thing we care about. So we need to know which leg is which with respect to that angle. So the adjacent leg is the leg that is touching that angle, right? The hypotenuse is also touching angle theta, but we know that the hypotenuse is the one that's furthest away from the right angle. So the adjacent leg goes from the angle marked theta to the right angle. The opposite leg also touches the right angle, but does not touch the angle called theta. And with that, we can take every possible ratio say take the opposite divided by the hypotenuse, take the adjacent divided by the hypotenuse, take the opposite and divide by the adjacent, take the adjacent and divide by the opposite, take the hypotenuse and divide by the adjacent, or take the hypotenuse and divide by the opposite, right? That is every possible combination of these things. You can put any of the three legs or of the three sides on the numerator and divide by either of the other sides. So you can have the opposite side divided by either the hypotenuse or the adjacent side. You can have the adjacent side divided by either the hypotenuse or the opposite side. And you can have the hypotenuse divided by either the opposite or the adjacent side. That's the only possibilities. We're never going to divide hypotenuse by hypotenuse. That's silly because anything divided by itself is 1. All right. But we take each of these things and we've given it a name. We call it the sine, the cosine, the tangent, the cotangent, the secant, and the cosecant. Right. Writing that down, of course, is a mouthful, so we're going to abbreviate all of these. And I do want to come back up to my picture to stress one more time that the actual measurements of these sides is going to depend on that angle theta. So when you have a different angle theta, you're going to have a different ratio. But as soon as you know the angle theta, you know which ratio you're talking about. So we're going to bake theta into the names of each of these ratios. Right? Sine gets abbreviated as SIN, and it depends on theta. So sine of theta is how we read it. It's function notation, but just the only thing that matters here is it depends on the angle. And then we have cosine is COS, tangent is TAN, cotangent is COT, secant is SEC, and cosecant, well, we can't use COS because we already used that for cosine. And so it usually gets abbreviated as the complete mess, CSC. And these are our 6 trigonometric ratios. If we know the ratio between two sides of a triangle, we can calculate the trigonometric ratio and we can measure the angle. But the way we're most often going to use it is if we are given the angle, we can figure out what this trigonometric ratio is and use it to solve from there. In days past, this was done by people literally with protractors and rulers, tediously drawing right triangle after right triangle and measuring them and writing all the information down on tables. It was called a table of values, and it was a several dozens to several hundreds page tome that had all of these trigonometric ratios set into it, along with a couple of others that have completely atrophied from the existence. For example, there used to be a ratio called the versine, VERSINE, which was simply 1 minus the sign that we have right here. Today we have calculators, and because we have calculators, all of those extra functions, all those extra operations have become less useful. In the days when you had to calculate things by hand, the more calculations that were done for you, the better off things were. All right, so we have the 6 trigonometric ratios, although we don't even need that many. Technically speaking, all we need is 2 of these to understand everything. But what I want you to look at is the way that I've set these up. Cosecant here is hypotenuse divided by opposite, which is just the reciprocal of sine, opposite divided by hypotenuse. Likewise, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So if we have just sine, cosine, and tangent, we actually have everything that we need. Cotangent and cosecant are very quickly dying off. There's not a lot of use for them, but in some specific corner case applications they come up, so I do want you to be familiar with it. Secant still has a good bit of power. If anyone is going to move onward to eventually study calculus, secant is going to come back and become very important later on in your studies. So it's worth remembering secant. It's definitely worth remembering sine, cosine, and tangent. Cotangent and cosecant, they exist. You might be in a career path where they're going to come up and be all over the place. You might be in a career path where you never see them again after these lessons. But as I said, used to be that we had these measurements taken very carefully, and you would look up the values of these functions in a table. Today, we don't need to do that, because if I switch my camera right to here and take a look at my calculator, you will see that we've got a couple of trig functions built right in. My calculator has sine, cosine, and tangent going across like this. It's also got on the same button sine raised to the negative first power, cosine raised to the negative first power, and tangent raised to the negative first power. And if you push the button a couple of times, it's going to cycle through those, along with a couple of others. We'll talk about sine to the negative first a little bit later on in this course. The sine with an h and the other one here, the sine with an h and a negative first power, are very special use. We're not going to get to talk about them this semester, but for anyone moving onward to study calculus, they will come up and eventually you will get to see them. All right. But if we have an angle, if we know a triangle, we can simply come here, grab our calculator, hit the sine button, punch in our angle, let's say 78 degrees, and the calculator is very happy to spit out the measure of, the measure of that angle. All right, we can do the same thing with cosine, we can do the same thing with tangent. And so I guess I should scroll my page down a little bit, and let's take a look at a couple of these just to get practice on how to use the calculator. All right, so for a couple others to look at, let's take a look at the cosine of 32.5 degrees. Which my calculator tells me is 0.8433, etc. And then I have the secant of 44.23 degrees. Now remember from the table that we were talking about, secant is hypotenuse over adjacent, which is the reciprocal of adjacent over hypotenuse. So secant of 44.23 degrees is 1 over cosine of 44.23 degrees. And that's how we can put it into our calculator. That's why the calculator doesn't need a separate secant button. We're going to hit a fraction. We're going to hit 1 in the numerator, and in the denominator, I'll punch in cosine of 44.23, which my calculator tells me is 1.39558. I'll round that and call it 1.396. All right. As I've been doing this, I've had some rounding that I've had to do on each of these. Most of the time, when you evaluate a trigonometric function, you are going to end up with an irrational number. There are a couple of exact values that I'm going to talk about in a future video, but by and large, when you are looking at a trigonometric function, you're going to be looking at an approximate value. When you're looking at the measure of an angle, you're also going to be looking at an approximate value, so I guess that makes sense. The rule for rounding trigonometric functions is a little bit clunky at first, but you can get used to it and it will start to make sense. If I have an angle theta in degrees, and then I want to evaluate the trig function for that angle. If theta is rounded to the nearest degree, then my trig function should get two significant figures. The precision of my angle determines the accuracy of my result. And for an angle given in degrees, we start with the nearest whole degree gives you two significant figures. And each digit further in precision gives you one more significant figure. So 10th of a degree gives you a third significant figure, 100th of a degree gives you a fourth significant figure, thousandths of a degree would give you 5 significant figures, but I've never actually seen that show up in anything involving trigonometry, so I'm not going to worry about it. The rules here make a lot more sense if instead of looking at degrees, we look at the other tool we have for measuring an angle, which is the radian measure. So if I set up theta in radians, then to the nearest tenth of a radian, 0.1, we get one significant figure. To the nearest hundredth of a radian, two digits after the decimal point gives us two significant figures. 3 digits after the decimal point gives us 3 significant figures. And 4 digits after the decimal point gives us 4 significant figures. Right? The number of digits after the decimal point when theta is given in radians tells us the number of significant figures. And because the conversion between radians and degrees is approximately multiplying by 100 to one significant figure. That's why it got shifted over to places, and the nearest whole degree gives you two significant figures. Right. For those of you who are moving onward, I've said it several times. For those of you who are moving onward to eventually take calculus, radian measure is going to become of vital importance. Radian measure is far and away easier to work with, and this is just one example of why that happens. But for a lot of engineering purposes, we work with degree measure. So for this course, cycling back and forth between degree and radian measure is going to become important. And our calculators can do that. So let me clear out some space. Let's take a look at a couple more problems, this time involving some radian measures. So if I want sine of 3 pi over 4, right, radian measures very often have pi in them. This is in fact an exact radian measure, but that's okay. Or if I have the tangent of 2.71, or if I have the, say the cotangent of 4.86. Well, I can go and pull up my calculator again, and I can set my calculator into radians mode. How to do this varies from calculator to calculator. On my calculator, I have a mode button right here at the top, and the first option has me cycling between degrees, radians, and the third option there is called gradients. I'm honestly not sure who uses gradients or where it's used anymore, but it was attempted to be a popular thing at one point. On my calculator, up here at the top of the screen, it says DEG. Depending on your resolution of your screen you're watching this on, you may or may not be able to read that. But the indication is always there to tell you what kind of measurement you use. So if I scroll over and go to RAD, you can see that that changes and it now says rad up there. And that's our sign that we're in radian measure. If I hit second and above mode, it says quit. That will take me back to the main screen. And I can start punching these in. Sine, I've got a fraction here. So 3 pi over 4 is going to give me, well, I gave it an exact value. It spit out an exact value, but I can, of course, always hit the approximation key here to get a decimal approximation for that. The other ones were given to us as approximations. I can take the tangent of 2.71, and my calculator tells me that the tangent of 2.71 is negative 0.46055, etc. Well, my rule says that when I'm rounding the result of a trig function where the angle was given in radians, I count the number of digits after the decimal point, and that's the number of significant figures. In this case, I've got 2 digits after the decimal point, so 2 significant figures is negative 0.46. And then for cotangent, again, cotangent is the reciprocal of tangent, so I'm going to punch this into my calculator as 1 over the tangent of 4.86, and my calculator will be happy to do that calculation for me. 1 fraction bar tangent 4.86. My calculator tells me is negative 0.1486, etc. Again, 2 digits after the decimal point in my angle, so 2 significant digits here, negative 0.15 is the value of that cotangent. All right, that's all I have for you on this one. So take some time, look at some practice problems related to this, and I'll see you in the next video.